Right now, start almost every lecture with a shout out to all my Ugandan followers and friends. I'll do my best to learn Ugandanese so that I can speak more clearly to you. All right, we're going to talk about kinematics today. And let me just be very clear about the ideas that I'm going to talk about here. Kinematics, I'll refer to by name. It is not physics. Kinematics is like any addicts. Maybe mathematics is the one you know about. Addicts means study of or properties of. It's not exactly like ology, biology, psychology. Those are different words. That ology is truly the study, the building of the knowledge of that subject. Addicts is more like, this is what it is. So I want to be very clear. Mathematics, kinematics, these are all studies of, but it's more like the properties of. When we talk about kinematics, we are talking about the language of motion. Kina, it's that root word there, meaning to move. Like kinesthetics. They even called the kinects. Chose that word for the Xbox purposely because you had to move in front of it. This is more like a jargon discussion where we're going to talk a little bit about the words and vocabulary associated with motion. They will carry us the entire year. But I also want you to understand that we're going to develop something called a motion equation, a way that we can mathematically model what we see in nature. It should be clear to you at this point from what you've already done using just the motion sensors that our goal is to find a way to mathematically model our environment. That is our goal. The words we're going to use here all have very specific mathematical meanings. And when I start writing these down, you have to understand that your meanings for these words are now meaningless. You need my meanings. And although some of these will be easy, some of these are going to be very challenging because you have some very deep-seated ideas about what these words mean, and they may not follow along with what I need you to know. I'm going to start with these 5 because they really make up the start for what we've been talking about so far today in class and yesterday. Distance, displacement, speed, velocity, acceleration. And they are the building blocks for the study of motion. The only other one I should put in here that I haven't is position. Because although a lot of people think that our motion detector was showing us the distance you traveled, it was not. It was showing you where you were as a function of time. You'll hear me say that a lot, a function of something. My belief is that you finished Algebra 2 and understand what functions are. You may not. So if you haven't, I will help by giving some kind of background whenever I deal with a function. So, I'm going to start right here at the top. Distance and displacement. They are distinctly different ideas. Displacement deals with position. In fact, by definition, it is the change in position. Now, some of you are pretty sharp, so let's see. Position is often denoted by a lowercase x. If I wanted to symbolically write displacement, what do you think it would look like? Got a couple of hands up. All right, yes, sir? It would be delta x, that's right, change in position. The delta symbol means change in, but displacement is a little bit more complicated than you might believe. Displacement is the absolute change in position. It is path independent. You don't know what that means yet. You will. It is path independent. I am hoping that this evening when you go to sleep, it will likely be in the same place that you woke up this morning. Let's assume that that's the case for almost all of you in the room, that you will be in the same bedding location this evening as this morning. If that's true, your displacement for the day is 0 because you ended where you began. That really doesn't tell us very much about what you did today. It merely states that over the course of the entire day, you had a displacement of 0. The reason I'm bringing that up is because the distance you traveled is path dependent. It is the length of the path that you took from your bed this morning to your bed this evening. If I'm using the same example, it is likely that some of you will get 15, 20,000 steps in. You might move 5, 6, 8 miles over the course of today. I don't know where you went, and distance can't tell me where you went. It can just tell me the length of the path that you chose to use. Earlier today, somebody says, if you travel on a semicircle, the path you took would be the size of that semicircle, that half of a circumference, while your displacement would be the diameter of that same semicircle. That's pretty good so far. As an example goes, that's all right. But distance is path dependent. If you're always going forwards and backwards over the same course, you are always adding distance to your pedometer. It's like the odometer in your car. The numbers never go backwards. They only go forwards regardless of the direction that the car is traveling. Forwards, backwards, left, right, east, west, north, south. Take a moment and maybe drop this into your notes. You got a ruler out, just kind of draft it out. It should only take a second. And then I have like 4 or 5 questions related to this. Remember, there was a red star on today, right? So today was supposed to be, just one of you guys give me the answer.
Person B.
Can you tell me why you know that to be true?
His position starts off like greater than the other person's.
All right, so his answer is perfect. We look at this, and the phrase I was actually looking for was the y-intercept. That would have been the best phrase, but I'll go with what he said, which is the person starts. Now, here's a word that's tough. Higher up is what he said. Let's be careful about that. The vertical axis is position. I really don't know what that means, though. What I'm saying is that forwards or backwards? Is that up a ramp of stairs? Is that higher on a ladder? I mean, we don't have the answer to that. So higher up is probably the wrong word. We know that this is the origin right here. That's our point of reference. All of our graphs always have a point of reference. It doesn't have to be 0, but usually for our graphs, the origin is considered 0. 0 meters away. Since position's in meters, this could be a picture of what you saw in class. They could have walked towards the door or away from the door. Meaning, reference is important. Higher, well, that's context. So we don't really know the type of motion. If I told you that these two people are having a race, which is what I said when I walked to the back of the classroom, higher doesn't mean much there, does it? Every race I've seen has been on pretty level ground. So I think farther might be okay. Higher might not be. We say higher because we're used to it going up and thinking up means high. But that's not really what's being depicted here. Because to the right isn't over. It's increasing time. Do you guys understand why I'm making these statements? So when we talk about the graphs, let's be careful about what they depict. I don't want to really call this the y-axis and the x-axis anymore. I will a little bit, because I think I have to, but I don't want to do it that much. So you said that person B starts higher up, but we mean it has a larger y-intercept. They are farther away from the origin at time 0. That's how I would like you to state this. This is a position versus time graph. There is a 0 point. When the clock started, that's time 0. That's the origin. So at time 0, person B here, person A there. A was closer to the origin, B was further away. B had the head start. All right. Paradise Falls. Somebody there needs to tell me the answer to question number 2, which is, who is ahead at 7 seconds? Can you tell me why you think person A is ahead at 7 seconds?
Because at 7 seconds, they have a greater coordinate.
First, I see no 7 seconds. Does anybody else see a 7 seconds? Maybe I'm missing it. So, but does it matter where 7 seconds is? Is person A ahead for every time after 5 seconds?
Yeah.
So 7 seconds could be there, right? The distance from here to there is how far away from the origin person B is. And person A is an additional amount. So clearly person A is farther away from the origin than person B. Any vertical line here could help you represent that distance from the origin. Does that make sense? So do we all agree now that A is always further away from the origin after 5 seconds? All right, now the next question is, when do the two objects have the same speed? Winterfell, you guys have an answer there?
At 5 seconds.
All right, this question is designed to elicit the wrong answer. And I am sure that a lot of you think it's 5 seconds. That is the desired wrong answer. Now, I want to be careful here. In problems like this, it's easy to jump on things. We have to kind of have an understanding of what we talked about yesterday and what's being depicted here to understand why this question is meant to try and trip you up. Yesterday, in the lab, we talked specifically about the idea that the slope of a position graph gives you velocity. And yesterday, we talked about the fact that velocity and speed are related. So, when I look at these graphs, do the graphs have the same slope at 5 seconds?
No.
Do they ever have the same slope?
No.
No. So they never have the same speed. The line with the higher speed, the line with the greater slope always has the higher speed. Do either of these lines ever change their slope? No. So who is always traveling faster? A is always traveling faster, even at 5 seconds. Somebody raise their hand and give me a single sentence that tells me what's happening at 5 seconds. Yes, sir.
Both A and B are the same distance from the origin.
That is a true statement. Would we all agree?
Yes.
A and B are both the same distance away from the origin. It's a great sentence. Can somebody tell me more? There's a little action. There's a little nuance. There is a little context. Yes, ma'am?
In the race, that's where they're like right next to each other.
True. One more thing. Yes, sir?
Person A is going to overtake person B in the race.
That's it. Both at the same position. A is overtaking B. Good? All right. Hard or easy? You say easy. On a quiz, this might have tripped a bunch of you up. If it was a 3-question quiz, I'm afraid I would have gotten a lot of 66%. Do you think so? I think so. I think so. I've given this quiz. So, let me ask you something. What if I added, say, person C? Here's person C. I want you to think for a moment. I would like you to tell me one thing that is similar to A and B about person C and one thing that is dissimilar about person C to person A and B. Talk about it at your table for a minute, and then we'll talk. How about Hoth?
They're both at the same place at 5 seconds.
There is a similarity. In this case, cyclist C also corresponds with all the other people. They all meet up at the 5-second mark. That is clearly a similarity. Thank you. How about Earth? You guys got one? Is there any other similarities? I believe there's one more similarity. It's okay if you don't have one. Any other table have another similarity? Yes, ma'am.
You never change the speed.
What's that?
C never changes speed.
Right, they still all have a constant speed. Would you all agree? Excellent. A difference. Who's got the one? There's one major difference about C than the rest. Who's got it? Yes, sir?
Going backwards.
Yeah, he's going backwards. You guys see that, right? So he's going towards the origin, everyone else is going back. That's the idiot running the wrong direction at the race. We don't like them very much. Okay, so the reason I'm bringing this up is we're tasked with mathematically modeling the natural world. That is the definition of physics. We want to mathematically model the natural world. And one of the ways we do that is to come up with what's known as a motion equation. The word motion equation is important to me. It is something that you may want to put on maybe a piece of paper designated for definitions or designated as vocabulary. Motion equations are special. They have a special form. And although I've been writing this all day, I think the nuance has been lost on most of my students, but they are functional equations that tell me position as a function of time. The belief is that if I know enough about the initial conditions and I understand what is controlling the object's motion, I should be able to make predictions about the future. That's our goal. I want you to think about what's printed just right here. This object has a constant velocity. Agreed? Yes. This object starts here, which I will call xi, the initial position. The slope of this line is the velocity. Which I'll use a lowercase v. If I bring all of that together, then it's not y that's on the vertical axis, it's position on the vertical axis. M is the slope, which we know to be the velocity. T is on the horizontal axis, which is where x is in the y equals mx plus b, so I'll put a t here. And finally, the object had a starting position, the location where it was at when t equals 0. This is a motion equation. If we assume that the object continues under its current circumstance, I can tell you where the object will be at all times in the future. Now, this is the most boring motion equation ever constructed, except for maybe it doesn't move at all. Now, this is not exciting, and I know it's not. In fact, this is the definition of mundane right here. But I want you to understand, yesterday you took simple data. You put the motion sensor out there and watch somebody move in front of or behind the motion detector. Bye, Summer. Now, that being said, I want you to consider, tonight somebody's going to go out at night, utilizing all their equipment and all their resources. They're going to map the night sky. They are looking to see if there's something out there moving that they did not see moving yesterday. If they find it, they're going to look at it again tomorrow and the next day and the next day. They're going to do the same thing your motion sensor and LabQuest did in 2 seconds over the span of weeks, attempting to look and see if that object that they have found can have predictable paths of motion. Can they create a motion equation for that object? And the reason is probably pretty important. If they find something moving out there, they're probably going to compare its motion equation with the motion equation of the Earth. Now, we do have a motion equation for the Earth. It is not simple. I know you think it's just going around in a circle. It is not. It is a complicated dance around the sun around our local supercluster of stars, our supercluster around our particular arm of the solar system, of the Milky Way, and then of course the Milky Way is also spinning. It's a complicated dance. And as we watch that dance unfold, there's a motion equation that describes where the Earth will be for now and for the next 150 million years. We're looking to see if there's ever a point where the position of this asteroid that we just found last night is going to be at the same place as the Earth at the same time. You do understand that could be bad for the Earth. Or it could be a pleasant evening and all we're seeing is a nice little, falling star. Or global killer. Who knows? A motion equation might sound mundane and boring, but you have to understand the idea is if I can get enough information, enough ideas about the initial conditions, I can make predictions about future events. Acquiring some motion data is important, but it's not the only thing. There's a lot of stuff that's going to cause that asteroid to move. I need to understand how all those things work together so that I can understand where the object will be in the future. My life could depend upon it. And if that's not enough to convince you of the importance of this one is a little different than one you just saw. Would you agree? Yes. All right, good. We agree. I like when we agree. Position. Time, A, and now this is B. All right. Please take a moment, 1 or 2 sentences that describe what's happening here, with special emphasis on how it's different than what we just saw. B does not have a constant slope. B's slope, is it getting steeper or shallower?
Steeper.
So those are the words I want to use here. B's slope is changing. I don't know if it's exponential or quadratic. I wouldn't know that unless I had more data. I know that it's getting steeper, and therefore the velocity is becoming greater. That's important. Now, the problem here is that it does not have a constant slope. That's important. That means the velocity is changing. And here's the buzzword that I do want to use. That means the object is accelerating. Technical definition here. Acceleration is the rate of change of velocity. Acceleration is the rate of change of the velocity. All right, I can't